Good morning, everyone. First, I would like to say thank you so much for being here for our presentation on the 12th Annual National GeoPrediction Competition here in Dallas, Texas. Our team consists of two members. I'm Tran, a graduate student at the University of Arkansas, and I am Dalton Hoffman, an undergraduate student at the university, and our advisor is Dr. Rick Kaufman. Starting with the project description of this competition, we are given an existing building resting on a mat foundation with a bearing of only 1,520 PSF. That has a current settlement of 29.5 inches at the end of primary consolidation. We are also given a proposed project adjacent to the existing building where they plan to make a 20-foot excavation and have a dewatering pump for getting the groundwater table out of their way. The challenge is to determine the additional ground settlement to the existing building due to the dewatering activities at the construction site 150 days and 285 days after the start of pumping. Dewatering activities will lower the groundwater table, causing buoyancy in the drawdown zone to be lost, and the effective stress that was being held in the incompressible water will get transferred to the soil particles, making them form into a denser configuration, therefore yielding this additional settlement. We are also given 3 boring logs with all lab-tested soil characteristics attached, boring B1, B2, and B3. The boring log B1 will be used for the settlement calculations because it's the closest to the settlement measurement location. From these boring logs, we're able to construct a soil profile as shown in figure 3. We find 5 layers consisting of a 7-foot fill layer, a layer of desiccated crust to be excavated, a 29-foot thick layer of lean clay and organic silts, followed by a 17-foot thick layer of well-graded gravel, and ending with bedrock 55 feet subsurface. Settlement is mainly caused by the thick clay layers. Therefore, in the calculation, we divide the clay layer into 4 sub-layers based on the changing undrained shear strengths within this layer. And also by comparing their Atterberg limits and water content results from past literature review, we believe the clay layer aligns closest with Boston blue clays. After constructing a soil profile, we worked on getting the soil parameters needed in the settlement calculations. The pre-consolidation stress was not given, so we experimentally calculated it following the Stoss and Caldwell equation. The over-consolidation ratio is approximately 1, so the soil is in a normally consolidated condition. Therefore, we use the normally consolidated settlement equation. In this equation, induced vertical stress is caused by the loads from the existing building and fill material. The induced stresses at the corner of the building is obtained by following Newmark's solution by multiplying the influence factor to the bearing pressure of the existing building. And being we know the total settlement and induced stresses, we can back calculate the compression index, and we can back calculate reasonable compression index and initial void ratio values that fall in a typical range for the Boston blue clays. After a few iterations of settlement calculations, these values for CC and E0 presented in table 1 produce a good match with the monitored result of 29.5 inches. A summary table of all the soil parameters used is presented in table 2. And once we were comfortable with the compression index and initial void ratio values, we rearranged the slope of the virgin curve to output a final void ratio at the end of consolidation. And these final void ratios are then used as the initial void ratio in the calculation of any additional settlement induced by dewatering activities. I will now hand this over to Ein for the determination of additional ground settlement to the existing building.
All right. Thank you, Dalton, for providing the soil profile and the soil parameter of the project. Now I will show you the method that we use to calculate the settlement due to the dewatering activities. So in order to calculate the settlement, we need to know the groundwater elevation at the measurement location. However, this information is not given. What is given to us is the groundwater elevation at the pump location and the distance from the pump to the measurement location, which is around 169 feet. So an equation of flow in a confined aquifer was selected to calculate the drawdown at the measurement location. So we select the Fudge aquifer because we have a well-graded gravel in the between of the clay and bedrock. We make an assumption of the discharge rate of 500 gallon per minute, radius of influence which is 2,000 feet, and radius of the wall is 0.5 feet. Because it's, the input information is not provided, so we know the distance from the wall to the measurement location. We know the conductivities and the thickness of the aquifer layer. So by plugging in everything into an equation, we'll be able to determine the water drawdown at the measurement location. And here's the result of the water drawdown at the measurement location. So after 150 days, the groundwater table elevation is expected to drop from 9.3 feet to 13 feet. And after 285 days, the initial groundwater table is expected to drop from 9.3 to 11.5 feet. The value was believed to be reasonable because the clay layer has a very low hydraulic conductivity, which is smaller than 10 to negative 8 centimeters per second. And the gravel layer at the measurement location is below the pumping elevation, so the water may not be able to travel upward to the pumping elevation. So we expected the water drawdown is small, and so as a settlement induced by the dewatering activities. Now let's move on to the settlement calculation. Same as mentioned before, the total settlement is the sum of elastic, primary, and secondary settlement. However, because of the short construction time, we only focus on, we neglect the secondary and only focus on elastic and primary settlement. Elastic settlement was calculated by on Giroux 1972. An equation was determined from here, on from the charge, and Q is the induced vertical stretch caused by the dewatering activities. E is the undrained modulus of the clay. Primary settlement were calculated based on the one-dimensional consolidation from Desagui. So after 150 days, the elastic settlement were expected to be 0.13 inch, and for the primary consolidation, by plugging in the CC and E0 values from the back calculations that Dalton had already mentioned, I'd be able to determine the total settlement. And based on the dewatering timeline, I'm able to calculate the degree of consolidation, and I find out the primary consolidation of 0.35 inch after 150 days. So it gave us the total settlement of 0.4 inch for both elastic and the primary consolidation. We're following the same procedure for the elastic and the primary settlement calculation, and have a total settlement of 0.44 inch after 285 days. All right, conclusion. So the accumulative settlement of the building due to the dewatering activities over 150 and 285 days is expected to be 0.4 inch and 0.92 inch. The settlement are believed to be reasonable because of the low hydraulic conductivity and high capillary effect of the clay layer. The pump discharge rate and the observation wall data are not provided. So if the data were provided, the calculation can be more accurate. Second limitation of the prediction is that the calculation was based on the empirical equation with many assumptions and engineering judgment. So a numerical modeling can be added to verify the result. Finally, we still believe that the settlement should be significant for this case because we have a thick clay layer which transmits the water very slow. However, if the project is constructed on a thick aquifer layer, we believe that we can reduce the effect of dewatering, the settlement caused by dewatering, by cover the excavation wall with a waterproof curtain, or we can build a relief wall to discharge the water to the underlying confined aquifer. So here's a list of the reference that we use for our prediction, and that's the end of our presentation. Thank you for your attention, and if you have any question, we are ready to answer. Thank you.